All right, so welcome everybody. Thanks for the opportunity to talk a little bit about quantum physics today. So this will be kind of a status update of where I am in my quest to try to prove that Einstein was right about quantum theory and that we can get rid of probabilities completely. I'm not there yet. It will take some more time, but we are making progress. Also, thanks to my students who have been working on the topic as well. I am aware that most of you do not know quantum physics. In fact, I designed the talk exactly for non-quantum physicists. In fact, I think I managed to almost not use any formula anywhere, and it's going to be purely visual. In fact, it might be even easier for you as non-quantum physicists to understand what I'm going to tell you, because that goes against the mainstream on many aspects of quantum physics. So a century ago, this is when all of that started. We thought in the 19th century that with Newton and Maxwell, we pretty much had everything that was needed to understand the world, but there was a few things that didn't quite work. And that led to discoveries after discoveries. And I think the most scary one, or I don't know if scary is the best word, or surprising or shocking, or is basically that when you throw electrons, actual particles of matter, through this double slit here, so it goes into two places, and then you look at the screen, you would expect to see two spots on the screen. That's absolutely not what you see. What you see is right here, there's interference, and it looks just like light. And that is absolutely shocking, because this is not light, these are particles, and yet we see these interference patterns, and it seems to not even be clear through which slit they actually go. It's kind of both of them at the same time, or so it's very confusing. And I insist, this is not light, these are actual electrons. So the whole thing about wave versus matter was thrown upside down. And that led to a lot of concepts that were invented over time as we made progress. So mostly in the early 20th century, but I think most of quantum physics was from the 1930s. So there came superposition, then entanglements, then the fact that the measurement changes the system that you look at, then the randomness and the probabilities all over the place, the spooky action at a distance, back to 1935 with Einstein. Rich Feynman, that many of you might know, at least by name, who gave great lectures, said that he can safely say nobody in the world understands quantum mechanics. I probably don't either. And what is absolutely the worst of it is that principles that we took for granted, like realism, the fact that when you look at something, when you don't look at the sun, it's there basically. So the realism principle and the locality principle, the fact that you cannot make changes propagate faster than light, well, you know, that's what it does to the cat. I mean, this is just terrifying. Basically, what happens to our understanding of the world in the 20th century. So I'm going to drive you through actually these concepts. I'm going to talk about superposition, entanglement, measurements, changing the system, randomness, spooky action at a distance. I'm going to talk about all of that, even realism and locality. And I'm going to give you a different perspective. It's not going to be the way that it's currently taught at universities, because we need to think out of the box if we want to actually come up with a theory that goes beyond quantum physics. But I still start with mainstream things. So for example, I just want to clarify, I'm assuming you all know complex numbers, right? So you can either think of a complex number as the real part and an imaginary part, but an even better way of looking at a complex number is in terms of the amplitude, how close it is to the center of the plane, and a phase, that's the angle around the origin. So you can either write a complex number as real and imaginary, or you can write it as the real number, that is the amplitude, how far it is from the center, multiplied by some phase that just makes it turn around, but the amplitude would still be the same. All right, following me? Just complex numbers. Now, you might have heard of wave functions. Who heard of wave functions? You at least heard the term. So this is the early way of looking at quantum physics. Nowadays, people think in terms of matrices and qubits and so on, which is just a lesser dimensional way of looking at it. But originally, it was wave functions. So what is a wave function intuitively? Well, very coarsely to begin with, it's kind of a probability distribution. If I look at one single particle in one dimension, just because to simplify things, then I might have higher probability of presence here. It might be here maybe likely, here less likely, here not likely at all, right? This is just a probability distribution over possible positions. that would be a real number, right? And then the area here sums up to 1 if everything is correct. I'm just putting in parentheses that technically it's actually the square root of the probability, but this is just a technical detail. So actually you need to square it to get the probability, but just a detail. We have this, but how do we get the complex parts? Well, this is the amplitude. We just need the phase. How do I visualize the phase when I think of wave function? Well, this is what you have in your gardens, the little spinners there. So imagine that at every single position here, there is a little spinner that has a color. Maybe it's red, maybe it's orange, maybe it's yellow, but it's periodic. This is why I like to see it in terms of color, right? So it's really between 0 and 2 pi. So if you imagine these little wind spinners, then this is basically how I visualize a wave function. It's basically made of the probability amplitudes, and it's made of a color. There is a hue at every point in there, right? So what you should see here is that the higher this is, the higher the probability that the particle is there. And then the color is a phase. And I now have to explain to you why we care about the phase. There's actually a reason for that. And to start with, I'm going to take a different distribution. So this is all over the place, right? But there are distributions that are kind of localized, meaning that it's almost 0 everywhere. And then there is some part of space where it's highly concentrated. So this is actually called localized. So this is what you would think of with a classical particle. You look at here, it's there, right? Like I'm seeing this computer here, like I'm seeing this table over here. So that would be localized, right? What if I let the system evolve now? I just wait and let the system evolve. When the evolution of the system, that's Schrödinger. Who heard about Schrödinger? Maybe through the cat, right? Schrödinger's cat. Well, it turns out he also gave his name to an equation. I'm not even going to show you the equation because you can think of it intuitively. What does it do, the Schrödinger equation? It takes a wave function with the high amplitude at some places, low amplitude at other places. But basically what happens is that when you have high amplitudes, the wind spinners, they turn faster. So they change color, orange to red to yellow to green to blue to orange, and so on and so on. So the higher the amplitude, the faster the wind spinner turns, and the lower the amplitude, the slower they turn. If it's 0, they don't even turn at all, right? So this is it. But what's going to happen if you start with this? Here, it might be the same color everywhere, for example. What's going to happen is that here, the spinners are going to turn very fast, and here, not fast at all. So what's going to happen is that the color is going to no longer be the same everywhere. What you get is a gradient. Even if you use Photoshop or software, you know what a gradient is. So we're going to get a gradient here that it's no longer the same color everywhere. And what happens is that because of the gradient of color that this creates, this is going to push the wave function left or right, depending on the gradient. So the higher the gradient, the more it's going to move. So basically what this leads to is that it starts evolving like that and spreading like this. So this is how the probability distribution spread. And now you understand that the goal of the phase is to make it move. Who gets that? Right? Because it creates these gradients of colors with the wind spinners. All right. But what we are looking at now is no longer the same as this, right? This we understand. It's like a localized object. We know where it is and so on. But this is a bit tougher to understand. And in fact, this is what quantum physicists call a superposition. Why do they call it a superposition? Because one of the ways to tell the story is that when you have a wave function here that has a non-zero value over all over the place, imagine something, the entire of Zurich, that the wave function spreads. So it's no longer localized as a specific, at a specific point. It's actually all over the place. And in terms of superposition, we kind of say it's here, but it's also there, but it's also in the main building, but it's also in that building over there. It's also in my office. It's basically everywhere. It's here and here and here and here and here. So this is quantum superposition. A door can be open and closed. A qubit can be 0 and 1 at the same time, right? So this is the concept of a superposition. So we have here the wave function that is formally a function from R to C, if we consider one particle in 1D. So this is just this line over here. So this is a function that associates every position with every possible position with a complex number. But I would like to shift your perspective here. And I'm going to do something very shocking. At least if there were quantum physicists seeing that, they would be shocked that I'm doing that, but I'll explain and I can give answers. I suggest that you do not think of it as an and. It's here and it's there. It's there. Think of it as an or. It's here or it's there. We just don't know, right? In fact, that's exactly how probabilities work, right? You have a probability of a coin being heads or tails. You just don't know, right? 1/2. But you just think of it as heads and tails. You think of it as heads or tails, right? So this is actually not very quantum if you think of it in that way. But this is a different way of thinking about it, right? You think of it, a superposition, as an or. It might be that the particle is here. It might be that the particle is there. I just don't know. But I did something else here. I'm no longer looking at this as a position here. I'm looking at this as a possible position. So now I'm looking at this axis right there as all the possibilities that the particle could be at. In fact, in terms of probabilities, this is an omega space, right? If you know your basics of probabilities, you have an omega space and you have the probability weights in there. And this gives us the probability weights. So this is an omega space with all the possibilities, and I'm not even thinking of it as a superposition. This is just, it's somewhere, we just don't know. So one way to look at it, if we don't know where it is in terms of possibilities, so possible worlds. What that means is if I have a wave function like this, that is distributed in one dimension like this, is that this is our world, Earth prime. If you watch, who watch sliders? Some watch slider. Earth prime is basically our world right here, where we are. So this is Earth prime, the actual world, and the particle is right there. Maybe we don't know. It's there, but we don't know. We do not actually, we don't see it, or we don't know that, but it's there. In another possible world, that would be a parallel world, it's here. In another possible world, it's here. In another possible world, it's there. But you see how I insist that it's or, it's not and. In one world, it is at one position. All of the positions, these are just possibilities. These are parallel worlds in which there's also you, but in a different way, and the particles are at different positions. And I was careful to kind of draw the points here in a way that kind of matches the probability distribution, because that means that there's a lot of world in which it's kind of here, and maybe less world in which it's at the extremities of the curve. Are you following? Okay. So these are the possible worlds. Now, I know that this could shock many quantum physicists, or at least at the bachelor's level, because when we explain the Heisenberg principle and measuring positions and speeds, it's not like that at all, right? But this is not something I actually invented, this way of looking at things. This is something that dates back to 1927 by a physicist called Louis de Broglie in France, and that was rediscovered in the 50s by David Bohm, another physicist. So this is known as the de Broglie-Bohm theory, and it is well accepted by the physicist community that this actually makes the same predictions as quantum physics. So it could be called an interpretation of quantum physics, right? But it's not mainstream at all. What it tells us is that when we have a wave function, there is an actual position where the particle is. And this theory, the de Broglie-Bohm theory, tells us that the particle is moving, guess what? Following the gradients. It's like a boat following the stream on a river. So the particle is just following the gradient, and it's kind of going where the wave function is going, right? But in one possible world, there is exactly one trajectory of the particle that goes all over the place following the stream of colors, right? There is one possible world. And of course, there are also all these parallel worlds in which the trajectories are different, but in every world, the trajectory is defined. And there is a pre-existing initial condition at the beginning of the universe that already encodes everything. This is called realism, right? It's already there, it's already encoding, and then the time flows. In fact, this is very Newtonian. This is very like physics was done even before. At least I understand that. It makes perfect sense to me that there is a position and the particle moves, right? Okay, I'm not giving you the equation. Don't worry about the equation. There is one, it's called the pilot wave equation, because the wave is guiding the position. Now that I mentioned these possible worlds and the slider series and parallel worlds and so on, I would like to share something very recent. I spent 1 or 2 years working on that, and I released it this January. It's a generalization of space-time that I call space-time-hap. The way it works is this. So space-time, as it was contributed in 1905, is made of space and time, and it's kind of together, right? It's space-time because it depends on the observer. They don't all agree on what time it is, right? So where I am would be space. What time is it would be time. So time can elapse. Right now I'm walking, it's a different time, and I'm at a different position. This is called time-like separation. And if I look at the lift right there and the table right there at the same time, it's space-like, right? So this is space-like separated or time-like separated. This was a revolution for causality. The idea that when there is causality, everybody agrees on the order of events, but when there is no causality, people might not agree. This is why going faster than light can actually lead to time travel. But anyway, this is space-time. What's very important is that it only describes our world, the world that we are in. Thus, the idea to extend it with parallel worlds as extra dimensions. Now we have time, we have space, and we have the dimensions that lead to parallel worlds. This is exactly like in the slider series where you open a vortex and you might end up in a world in which the Egyptians took over the world and there's pyramids in the middle of New York, right? So these are parallel worlds. So the way you think of it is that you have time in one world, time is elapsing, or space with some objects that you look at the same time from your perspective. But there is another dimension that basically corresponds to that vortex that you go to parallel worlds in which things are just different, right? So these are parallel worlds. This is space-time-hap. Hap comes from happenstance, right? It's a word you might have heard from also in movies, you know, the wings of the butterfly that cause the storm and so on. So I call it space-time-hap, all right? So again, the best intuition you could have is the slider series, right? You can just go to parallel worlds and not just stay in our world. Okay. All right, and now if I bring that into perspective, this is hap, right? These are different possible worlds, and this is hap. What's very important to understand is that these are not the same worlds. We are in one world, this one. There is a name, by the way, just so I say that. This is the actual fact, this is our world. These are called counterfactuals. These are other ways things could have happened. For example, there is one world in which Switzerland is still under Napoleon. Maybe here, this is a counterfactual. This is not our reality right there. Okay, so now that was superposition. Let me go to entanglement. In order to understand what entanglement is, think first of it classically. Instead of considering positions on R, I'm just going to consider three possibilities. It's simpler. So instead of R, I'm just taking a set with three elements. The particle can be here, or here, or here, right? And then the wave function for this would just be three complex numbers that just assign a specific probability to each one of the possibilities, and let's not care about the color right here. Now, this is one particle. Until now, I only showed you one particle. What about two particles? Well, two particles in the 19th century, that's how you would think of it, right? This particle has these three possibilities. This one has these three possibilities. They have this probability distribution. So this is the Cartesian product, right? C to the power of 3, C to the power of 3. So there are 6 degrees of freedom, right? There are 6 values in there. And this is just the product, right? For example, this here is the multiplication of this by this. In fact, if you know probability theory, this is just a probability distribution in which the two variables are independent, right? You can just express probability of AB as the product, probability of A times probability of B. What entanglement means in quantum physics, or at least 80% of the entanglement, is that instead of the Cartesian product, you do something scary that's called the tensor product. What does it mean? You no longer require the variables to be independent. Now you can have anything in there. And what you can thus have could be that now you have very high probabilities that they are at the same place and very low probability that they are not at the same place. This is called, this is a dependency, right? The conditional probabilities are not identical to the marginal probabilities. This is in fact entanglement. 80% of it, there is something more to entanglement that I'll come back to, but in essence, understanding quantum entanglements means understanding that you don't have 6 numbers, here you have 9, right? You specify these 9 numbers separately, and you can have dependencies across the variables, right? So this is now how we can say we have 2 qubits, and it's 0 and 0, or it's 1 and 1, so it's entangled. All right, so now, if I don't use 3 in there, that was just a simplification, but I come back to R, then that means that if I look at the wave function, now instead of R1, because here I had R1, right? I had only one dimension here. Now I have 2 dimensions. So that's not a 3D screen. unfortunately, so I cannot show you the 3D of that. So what I'm showing here is seen from above, right? So I have these 2 dimensions, and I'm looking from above, seeing that here it's a high probability amplitude, think of it of going outside of the screen, and here it's very low. Like this is a mountain, and these are planes in there, right? Entanglement means that there's a dependency between the 2 variables, and we're going to have a probability amplitude in 2D here that is basically diagonal. It's not just the multiplication of the 2 dimensions, it's really a tensor product, so going diagonal like that, right? Are you following me? That's called entanglement. 80% of it, again, there's one more thing to entanglement that I'll come back to later. All right, now let's raise the number of particles to the number of particles that there would be in a table or a chair, so an everyday object. This might be known as the Avogadro number to some of you, 10 to the power of 23 atoms, typically. So this is why I put 23 zeros in there, just to imagine that this line right there, that used to be a single dimension, has in fact quintillions, sextillions, heptillions of dimensions. It's absolutely gigantic space, and there's a probability amplitude and some colors on that. What entanglement might mean is that all of the configurations of particles in which they're all together at the same place have high probabilities, and those in which they don't have low probabilities. Right. So you might have now a closed door and an open door because there's a high probability for the entirely open door and a high probability for the entirely closed door, and all the rest is just almost zero. So that's called an entanglement. All right. Are you still following? Yeah. This one?
So I wonder why we have the diagonal with the highest probability. Is that a theorem, or because it seems to me like it's like a covariance matrix, right? But the diagonal means low covariance instead of high covariance. And you said that instead of being independent, they actually have some correlations. And to me, it seems that the correlation is not that strong.
Okay, so let me be very precise on what I'm saying here. I'm not saying it has to be this way. I'm just saying it can. What I'm saying is that if you look at it from a classical perspective with 2 independent variables, that can never happen. That you cannot express as the product of 2 marginal probabilities. Here you can. What I'm saying is that if you constrain yourself to the case where the variables are independent, this is very limited. This is classical physics. And what I'm saying, what makes quantum physics quantum, or part of it, is the fact that you relax that, you no longer require that this is independent, and you allow that it can be entangled and leads to this kind of situation, right? And absolutely, you can actually define entanglement as a correlation here. It's not the same thing, in fact, these 2 things, entanglement and correlation, and I will come back to the difference. But fundamentally, at that point, you can actually view entanglement as a correlation in that sense, that you allow for correlations. But there is nothing that forces that correlation. In fact, the only way you can force it is by preparing a system with that correlation. Right? So a physicist can prepare a system of 2 qubits that are 0, 0, and 1, 1. But you're not forced to do that. There is no obligation to do that. It's just that we can do something that we couldn't do before. Right? Does it make sense? Yeah, we can also talk offline more about that. Yeah, but this is just more degrees of freedoms. You can do more things. You allow for that sort of things to actually happen. All right. Any other questions? Yes.
Oh, just a quick question. If I understood the thing with the phase, with the color, right? So in my mental image here, basically, so the distribution is basically the probability that, here the probability that something like a particle is at that position, and the color or the phase is only kind of expresses how it will evolve over time.
It's the dynamics, yeah.
Okay, and so the phase is like the probability is independent of the phase. Only like the evolution of the like at one point in time, the probability is
Yep.
independent.
Yes. If you only look at a snapshot, you forget about the evolution. You just look at a single snapshot at time t, then the phase doesn't matter. The phase plays a role in the dynamics because this is what moves the whole thing. Yeah. Mm-hmm. You can view this phase, in fact, as interferences. What's going on is interferences, which is an awesome transition to what I'm going to tell right now. Because now I'm moving to measurements. So you might have heard you can measure a quantum system and that kind of change what the system is at. But let's define formally what we mean with measurements. So let's simplify where I can measure in two ways and I can get a 0 or a 1 out of the two. So the way that physicists think about that is you prepare a system in some quantum state, so wave function, probabilities and colors, and then you're in your lab as a physicist and you can choose to either put the device on A or put the device on B. It's like a switch, a master switch that you have, and you can pick A or B. This is your choice as a human being, free choice, right? So you pick A or you pick B. And then what's going to happen is that you press some button that activates the measurement, and then the machine maybe roars and does something to the system, and then you have a pointer with a screen there that will show 0 or that will show 1 after a while. It might be a pointer with, like in the 19th century, with an actual, an actual arm that moves, but it can also be pixels on your screens. It's the same. But it is macroscopic. What's very important is that you're looking at a device, be it your screen, be it the pointer and so on. It is 10 to the power of 23 particles, right? And that you see either go to 0 or go to 1, right? This is a measurement, right? Is everybody following? All right. Now, what we hear a lot about measurements, and that the mainstream view, is that there is a collapse of the wave function. If you measure the particle to be somewhere, that changes the wave function to actually collapse to just the position where you see the particle to be. This is the mainstream way of looking at it. Not everybody agrees, but this is one way of looking at it. But the way I will now explain it is different. I'm going to explain it the way that Louis de Broglie and David Bohm explained it, in terms of this following the stream and surfing on the colors. So basically, when you do a measurement, is that you start with the system like this, on this gigantic, like the whole universe. Imagine the whole universe that contains both the system that you're measuring and your computer screen and your measurement device, everything, right? The pixels on your screen that will show 0 or 1. What's going to happen when you do the measurement is that something is going to happen. It still interferes here because it's in one piece, but then it starts separating there. So there's interference because of the colors. So it interferes there. But then after a while, it separates. It's a dynamic evolution. The system forks into two partitions in the sense that here it's almost 0. For all practical purposes, it's basically 0. And now we have part of the wave function here and part of the wave function there. It means that in many of the possible worlds, we actually see the pointer showing 0. And here in many of the possible worlds, we see the pointer showing 1, right? And I put these possible worlds in there. These worlds here are extremely unlikely. The probability is borderline 0. You can forget about them. You only consider those for which the probability is actually bigger than 0, right? So, for example, it could be because of the area of the two curves. I told you the area gives you the probabilities. We have 1.5 chances of being here, 1.5 chances of being there. Let's assume we are here. It means this is Earth prime here, and we see a 0. And the way to think about it is that in some parallel world somewhere else, maybe with the Egyptians, with the pyramids in New York, they actually measure a 1 in there. Right? Maybe even closer to you, just yourself measuring in 1 in a parallel world. What's very important here to understand is this is disjoint. There is now a hole in there. There is a 0 probability plane in there. And the number of dimensions is so absolutely gigantically enormous that the odds that in the future, the wave function evolves in such a way that they meet again is negligible. That will not happen. This is just impossible. It's probability 0. So this is called is decoherence. It decoheres, and now you really have a fork of the worlds with worlds in which you have actually recorded 0 in your book here, and worlds in which you have actually recorded 1. This was the way that de Broglie explained it. Now, those who say the wave function collapses basically mean that now you forget about that part, and you only look at that part, right? So even Louis de Broglie is able to describe the collapse in that way. So now if I come back to this theory with the particle following the colors, what's going to happen is that now the wave function will regularly split every time you do a measurement, and it's basically forking into possible worlds. We are here, and we always knew that we would be here because of the initial conditions right there. We're just following the flow and we are here, but we could have been there if we had another initial condition, right? Does it still make sense? So every time we measure, the universe forks into subparts. So the way you can draw it is in this way with these pipes, right? That you can think of processes, if you're a computer scientist, processes that fork, right? So basically this is a PID and that's another forking PID and so on. And then you get all of these worlds. And there's still several of them because it's going to continue to fork and fork and fork again in the future, right? But everything is known from the very beginning because these are perfectly well-defined deterministic trajectories. All right, this is called the many worlds interpretation by QB average. Now, how do we know there is entanglement? We have a problem because we are only in one of these worlds. Maybe we are here. How do we know what's happening in the other worlds? We don't. We have a theory, but we don't. We have no access to these worlds. We only have access to what we actually do in our world. You only have access to the zero that you found here. You don't have access to this, right? Maybe unless in science fiction, but we don't have access to this. It's a possibility in some alternate world. We only have the zero. So how do we confirm the existence of these entanglements? How do we do that? We do this like this. So imagine that I have entanglement of two particles like that, and now I measure. What does it happen when you measure? It splits, it forks. So this is what it does. It's seen from above, right? This splits into these two parts. There is one part in which both of the pointers for particle A and particle B show zero. And there is in some hypothetical parallel world somewhere else, they will both show one. Now you see there is some correlation in there. But how do you see correlation? We only did it once. So there's no way to tell yet. The way you do that is by actually repeating the measurements. You do it 1,000,000 times and you record them and then you measure correlations. But let me open a parenthesis before I go into that. What happens here when you have these two particles that either both leads to zero or both leads to one is called a counterfactual dependency. The proper way to talk about that is using the subjunctive conditional in English. Alice measured zero, Bob measured one, maybe far away. If Alice had obtained one, which happens in this parallel world, then Bob would also have obtained one. So you see, this is not a causality thing. It's a counterfactual thing. It's a reasoning about parallel worlds. Einstein knew this. And I don't know if many people notice, you can actually read the original paper. Einstein was using the subjunctive conditional. This is extremely important. If instead we had chosen another quantity, right? He doesn't say we changed the quantity. He said, if we had chosen another quantity. This is super important. In fact, he explicitly said no real change can take place in the second system in consequence. So this is not a change. This is a hypothesis, hypothetical, different things in another world. But let's come back to these repeated measurements now, closing the parenthesis. So we have a system with this wave function. We do one measurement, it forks. Let's do another measurement, a second one, it forks again. Let's do yet another one, it forks again, right? Now, these are a lot of worlds that we are in here. This is the actual world. The actual world is somewhere in this mountain right there, right? And we have a book, an actual record keeping, a file, a data set, where we record the first time 0, 0, the second time 1, 1, the third time 1, 1, and so on. This is how we see the correlations. We see the correlations because we did it repeatedly in the same world, and these are correlations and not entanglement, because this is actual statistics. You write them down, and you use classical statistics to see that if you do it 1,000,000 times, there is some covariance between the two variables. This is statistics. This is another world in which the log is different, but in all the worlds, or almost all of them, you will typically observe a correlation. This is how we actually notice that there is entanglement. It's indirect. We don't have access to the parallel worlds, but if we repeatedly measure, then we see the correlation. Okay, Now, I told you correlation is not the same thing as entanglement, and there is a tiny little difference between correlation and entanglement. Because if all I tell you is entanglement is correlation, then that would make things easy because quantum physics would not even exist. We would be doing classical physics, right? If it would be that simple. The one thing that makes the thing truly quantum is that you have this switch that you can act on. Here, we didn't use the switch. We just kept the switch on the 0-1 way of measuring. Imagine that now I can either measure 0-1 or I can measure AB. If I measure 0-1, I get a 0 or 1. If I measure AB, then I get A or B. So now let me make the thing more complex and say that now we can measure using the switch one way or the other. What makes it truly quantum, and here we cannot explain it, or so it seems, with pure correlations, is that even if we change with free choice that switch, we still get the correlations there. And John Bell and many other people, so here it's at ETH, Renato Renner's group, they showed that classical correlations alone cannot explain that this also is true if you actually can change freely the parameters of the measurement. This is absolutely truly quantum. Yes?
So why instead of why they are using correlation to explain instead of just use it as a characteristic and value?
So there's two ways in which I can understand your question. The first thing is, why not causation? Because the two people here might be far away from each other, you know, maybe on Mars and on the Earth. So this is really something that happens at the same location at the same time for one observer. But I'm not sure if you might not have meant somewhere else. Like I basically started with the premise that there is a correlation here, right? And then said, okay, now we measure a correlation. But there is a difference. This we cannot observe. This is totally inaccessible to us. This is purely theoretical. The one thing that we can observe, we cannot go to parallel worlds. The only way we can observe things is by repeating things, logging it into a book like this, and then running statistics on there. That we can, as human, observe. The rest is inaccessible. This is pure speculation, but you can use this in order to infer things. Because since this is true, right here, this is actually breaking an inequality known as Bell inequality. What this shows is that if you can freely choose your A, B, or 0, 1, you cannot possibly get that record. Basically, this record is breaking the laws that regular probabilities would tell you if you assume that you cannot tell in advance which measurement I'm going to do. Right? This is why we know it's truly quantum. You cannot explain that purely classically with free choice of measurement. Did I answer? We can also continue offline. Yeah. But what's very important is that all of these experiments, they don't even involve quantum physics. When you do that, this is purely using probability language with correlations. Then there is an inequality expressed purely in probabilities. But then you can just prove that there is no way you can actually get that recorded in a book if the explanation of the system doesn't involve quantum, but it's separate. Yes?
I was wondering, like, the switch, the A and the B, that's kind of just, it just kind of, does it just change kind of how we see our output? Like here, for example, like the A or B, like what is kind of the effect of this switch on the outcome of these, or not of the outcome, but like what we record the experiment, basically?
So you used the word change and the word effect. So it's actually very good because I'm going to be focusing from now on. This is exactly what I'm going to get into. It's very important to not think of that in terms of changing the switch. You're making a choice. You're either putting the switch here on making the 0-1 measurement, or there making the AB measurement.
But AB is just the labels on the output.
Oh, yes, let me tell it otherwise. You could always call it 0, 1, right? It's just that if you put the switch on the right, you would interpret that as an A and that as a B, right? But it's still the same pointer. You're just doing something different to the system.
Okay.
So either you put the switch on A and you see the pointer here and you get a 0, but you could also have gotten a 1. Or you put the switch on the right, meaning that you're measuring something else. Now you can get small a or small b. Now, if the pointer is here, you're going to interpret that as a small a, right? You could add a or 0 here if you want. And if it's there, you interpret that as a small b. It's like measuring the speed or the velocity of a particle. This is like, I want to know the position, and here I want to know the speed.
Okay.
What's important is you make a choice. It's only one of them, not both. Yeah? Okay. Yeah, David, you had a question too?
Yeah, so I'll just give it quickly, but 50, possibility result with the going you're assuming that an independent choice
Yep.
is possible.
Yes, not just possible, that it is the case.
But like, it can equally just be a proof that that's not possible.
Yeah, this is exactly what I'm getting at. This is exactly the loophole that I'm actually putting myself into. That's exactly it. These proofs are indeed assuming that whoever controls that switch, either I do the 0B, 0-1 measurement, or I do the AB measurement, whoever controls that switch is a human who has free choice and is unpredictable. There is no information in the past about what they're about to do. If that is the case, then you cannot possibly get this with a classical explanation alone. Yeah. Yes? Which slide are you on? Yeah. Oh, this is just simplification. Doesn't have to be 2. Can be 3, can be 4, can be a very large number. In fact, it's very interesting because this way of splitting in 2 started 20 years ago with quantum information. In fact, quantum information, we started splitting things in 2. The reason for that is simply that it's enough to get quantum stuff. We can actually just do reasoning, just splitting in 2, and we get all the quantum effects that are desired. This is exactly why wave functions are kind of losing in momentum, and now we just think of qubits. If you use qubits, then it just splits into every time. Yeah.
That one is Stephen Hawking's fault. He had a diagram in British which looks like a big crowd.
Yeah, that's possible. Yeah. Yeah. But I'm not assuming just it can be 3, can be 4, can be anything. Yeah. Okay. Let me go back. I don't have so many more slides actually, because now I'm getting to what I'm doing now, is that because these impossibility theorems rely on the fact that whoever moves the switch makes a free choice, many people think we have to stick to that assumption and deduce that we give up on realism, we give up on local realism and so on. I interpret that differently. I'm saying maybe there is no free choice in that sense of who moves the switch. Maybe, in fact, what we should do is add the choice of the switch in the forks. Meaning that we should do is that we also fork the universe on whether I put the switch on the left or the switch on the right. Then on the left, I get 0 or 1. On the right, I get A or B, right? But what's very important is that if I do it once, in my book, I only have one single record, right? And I still need to repeat to get an actual log. But now, what's very important is that if I'm on the left here, AB is undefined. If I measure according to 0, 1, I measure the speed, the position is undefined. If I measure the position, the speed is undefined, right? This is very important. What is defined is only what I actually measure. Now, that doesn't work. I have to come back here. What's happening is that also before, right? Before I got the results, it might have been predefined what 0 or 1 was. That's actually what Wiedeboy was saying. But AB is undefined here, and here 0, 1 is undefined. Now, how do we turn that into game theory? That actually looks a lot like game theory, doesn't it? Because here, this is basically a decision by me as a physicist to put the switch on the left or on the right. And here, this is a decision of the universe to tell me 0 or to tell me 1. This is in fact decision theory, it's game theory. So we can redraw the whole thing as a game like this and interpret that as game theory, yes?
when you were talking about the free will, like free choice of measure 0, 1, or 8, so do you mean there is no effect from the initial condition, or there is like?
You could put it that way, yes. The one way to think about free choice, it's very unnatural to me to think in this way, but the way to think of free choice in that way is exactly that. There is nothing in the initial conditions that tell anything about your choice. It's like every time you make a choice, it's coming from outside. It's as if, as a human being, there was something outside the universe that would contribute information.
I see. Okay, that would ignite another way of discussion, like what is free will anyway?
Exactly.
Can you explain that your choice is complicated?
Yeah, but I'm not even going in philosophy. My definitions of free will, they're purely mathematical. Basically, we are saying that there is no information in the initial conditions on your decision. That's purely formal. But I think this is the hypothesis we should change. And this is why instead I'm suggesting it should be in the initial conditions. Now it is in the initial conditions. We humans are part of the universe. We are also quantum. We are also part of that. And this is why I'm saying now we can turn it into a game where at some nodes of the game, you, the human, make a decision on what to look at, human or whatever system you consider, and then the universe answers. And so any quantum experiment, you can reformulate like this as a game. Yes? Yes. The winning, basically, that's the numbers over there. These are called payoffs. And this is assuming that you optimize something, which raises the question, what does the universe optimize? But in fact, the universe optimizing something is not new at all. We've always been looking at science that way. You might know the principle of least action. When you consider the path of light, light is always taking the shortest path. So nature is optimizing something. So the things that go in there, for now, these are just model weights. So I don't know what to put in there. This is the next step of my research, right? But here, these are known physical principles that nature is optimizing things. But the novelty here is that it's optimizing things in competition with other agents that also optimize things. Does it make sense? Yeah. But this, I don't know what to put in there. This is exactly my future avenue of research. These are just model weights, like the ChatGPT model weights, if you want. I need to train that thing in order to reproduce the actual predictions. But what we found out with students of mine with whom I worked is that Nash doesn't work. If you try to solve that game with Nash, then you're in fact back to the fact that there's free choice. Because in Nash, you have to define your choice no matter what. So it means that it comes from outside. But in the case where you give up that definition of free choice and you consider it's part of your original conditions, it completely changes the algorithm that you use to solve the game. Look the way that it happens here. If I play the game, I keep eliminating possibilities here. And then at some point, I start concluding it goes to the left and I keep reducing. This is a forward induction, goes top down. And that actually gives me, if I find the right model weights, a theory that tells us exactly what my measurement results will be, deterministically. But it takes a game theory resolution algorithm to actually get there. And Nash just doesn't work. If you do Nash, then you are stuck with this free choice assumption, and then you are stuck with the Bell inequalities. So you cannot make any progress with Nash. This is why we need a non-Nash, meaning that we weaken free choice to get that. I'm almost at the end of my talk. I wanted to give you this wonderful quote by Sir Arthur Conan Doyle in Sherlock Holmes, because this is what we do here. We eliminate possible worlds. How often have I said to you that when you have eliminated the impossible, whatever remains, however improbable, must be the truth? We basically proceed with elimination of all possible worlds until one possible world remains, and that is our world. That is the goal of the theory. But again, I don't know the model weights yet. I need to figure out the model weights. So now I'm going to give you a take-home message to leave this talk with, that I hope, I'm trying to communicate that to data scientists, but it's an uphill battle. Relativity theory revolutionized causality. Information theory revolutionized correlations. Quantum physics revolutionized counterfactuals. Right. This also goes hand in hand with space-time-hap. Right. Time is about causation. Hap is about counterfactuals. It's the parallel worlds. Space is about correlations. Why? Because correlations is something recorded in a book. right? This is why it's space. Now, here's the takeaway message. People confuse these three. They confuse causation with correlations with counterfactuals. So the first one you probably know. This is the Nobel Prize chocolate diagram, right? So I'm sure everybody understands that causation is not correlation. So this one I pass very quickly, I know you know. But here's the weird thing. People willingly conflate causation and counterfactual. In fact, if you look at what was done by Lewis, Hume, or Judy Pearl, we define causation as a counterfactual dependency. I define causation as in if I act on something, that's the do operator, that changes something that leads to the desired change in effect. So you define causation as counterfactuals. This is an approximation of reality. These are not the same thing. This is about time. This is about hap. And the third one that people confuse counterfactuals and correlations is also all over the place. This is when people basically use conditional probability notations, not for the data recorded in a book, that would be actual correlations. They use it for parallel worlds. So very often you find in literature that we use this conditional probability notation for something that in fact is about counterfactuals and parallel worlds. But because of the Bell inequalities, this is all over the place. And people often say casually, there is no omega space. We basically write down these conditional probabilities, but there is no actual omega space that makes them well defined. So what I'm saying here is that this is different. Counterfactuals are not correlation. So again, causation is not correlation, is not counterfactuals, is not causation. That is the one takeaway message I'd like to leave you with. And finally, finishing with this quote, long may Louis de Broglie continue to inspire those who suspect that what is proved by impossibility proofs, like the Bell inequalities themselves, is lack of imagination. We should not give up the idea of getting rid of probabilities to explain nature better. We've been doing that for thousands of years. There is no reason why we should give up today. So this is what I would like to leave you with. Thank you very much. That's a thank you to my to two students who contributed a lot. Yeah. That's it. I'm done. So if there are questions, I can answer them and also take it offline. Yes.
Basically, this wave function was also determining the sort of the density of the hap space or the hap world. But then I was thinking, well, you can actually prepare, you can actually entangle particles. Which means that with the definition that you are sort of finding as two specific wave functions where the probability is of the two events happening together is at this diagonal. But that would mean that you are moving in the hap axis for finding that specific those two specific wave functions that produce that sort of correlation. So I wanted to see your take of what this preparation would mean in that sense. So would it be moving in this hap axis, or because otherwise there's this problem of what is defining what.
Mm-hmm. So let me give you three elements of answers. The first element is that you are correct that when you look at a wave function, you should consider it as a distribution over hap. It's a density of probability over all possible worlds on an omega space. That's exactly how I view it, and in that, this is correct. This is on hap. The second thing is that you said two wave functions, but they are not two wave functions. That's exactly, in fact, what we are saying here. There is only one wave function. There is only one wave function that is defined on the Cartesian product of all particles. This is why we get this 9 here. There is only one wave function. The two-wave function is the specific classical case where you do not have any correlations. There is only one wave function over all of the particles. Hap is not just R3. It's not just space. Hap is R to the power of 1 followed by 23 zeros. It's absolutely gigantic. This is a configuration space. Hap is every possible way the molecules of the visible universe could be at. This is beyond our imagination, basically, to think the size of that. And there was a third thing I wanted to to say, yes, about what's to be very, very careful with. How do you reason about hap? A lot of people use the word change when reasoning about hap. A lot of people say, if we change the switch from A to B, you should never do that. You're not changing the switch from A to B. You are either putting it on A and B, but then you don't change it. You only hypothetically imagine what would have happened if it had been put differently. This is not a change. This is a hypothesis on an alternate reality. This is super important. I think that language constrains us. It is precisely because we use the wrong word or we use specific words that it constrains our mindset and it prevents us from thinking outside of the box. So what I'm saying is we should not call it a change. We should use the subjunctive conditional, what would have happened if it had been put in a different setting. Does it help? That's the three things.
Yeah, and what about the preparation of entanglement?
So the preparation, this is basically this first thing you do right there. What is very important to understand is here there's the idealization. When we talk about preparation, it's the mainstream quantum physics way of looking at things is that we are outside the quantum system, and we are preparing a wave function for a specific system, but we're outside of that wave function. And there's a lot of philosophical debates in that, like Wigner's friend, for example, is what if you are inside the wave function, right? So it's very tricky to actually describe that because if either you're outside or inside, right? But if you're inside, then what you prepare is also predetermined by the initial conditions. Does it make sense?
You can't actually entangle particles, and you can't measure that they're entangled. You can't do either of those. What you do is you select particles that you know by construction will be entangled, indeed, because they're fundamentally related.
I think it's a good way of putting that, yeah. Mm-hmm. Yes?
I just have a simple question. What is the cardinality of this space? That's not on the screen, right?
Oh, that's what it's here. So if you look at the visible universe, there's 10 to the powers of 80 particles. So it means that we are literally looking at r to the power of 10 to the power of 80 times 3 because there's space. This is beyond what we imagine. And if the visible universe is only one part of it and it's even bigger than that, then it's just gigantic.
Is the many worlds theory like the only commonly accepted theory, or
there are many, many, many competing theories, so plenty of them. Yep. Among others. It's also based on the broglie-bohm theory, right? So here's the thing. All the interpretations of quantum physics, they are equivalent. In fact, this is the reason why there are philosophical debates. They're all equivalent. They all lead to the same conclusions. So it's only an interpretation. This is why we call them interpretations. The many worlds is also an interpretation. The Bohm theory could also be imagined as an interpretation, right? Because we don't have access to the initial conditions. But what I'm trying to do here is not just an interpretation. I'm trying to find an interpretation of quantum physics that allows us to circumvent the loophole that prevents us from extending quantum physics. What I want to end up with is more than interpretation. I want to end up with an extension theory that tells you exactly each measurement what it's going to be. That's my goal. I don't want to contradict quantum theory. I fully agree with the predictions. I just want to extend it. Yes, more questions? Go ahead. This is not enough. So what I can do, because it's very interesting, I can send you a pointer to a paper, a note that was written by Roger Kolbeck, who was a postdoc of Renato Renner, who explains how you build the Bell inequalities. It doesn't require much knowledge of quantum physics. It's beautifully mathematical, purely based on probability theories and conditional probabilities. So if you want, I can send you the link. it's beautiful. It's a beautiful explanation of things. Basically, the idea is that if you look at all possible probability distributions, it's kind of a cube. And what happens is that when you introduce constraints like free choice, you're restraining the subset of the cube that is accepted. And so if you assume free choice, you have to have the distribution on omega in a simplex. I think it's called the simplex. But in reality, you measure correlations that are outside of the simplex that would correspond to these assumptions. So it is proof that there is something more to it. I can send you the link if you want. I think you will enjoy it. Any other questions, or should we leave it at here?
Can I have a question?
Oh, somebody on Zoom has a question.
Yeah, it's Michał.
No, we can't.
Hi, Ghislain. I managed to join. Okay, hi, Ghislain. It's me, Michał. I managed to join. So my question is, have you thought about, because like the universe is constantly forking, have you thought about why is it forking and why we have so many choices? So why it's basically going with time to many more worlds, and how it might be connected to entropy?
So the question, well, that's a big question. I'm not sure I will be able to answer, but let me repeat it. So the question is, why is it that the world is actually forking, like I showed you? Why is it continuously forking? And what does it mean in terms of entropy? I'm not sure I will answer the question in the way you expect, but let me just say one thing. There is a beautiful book by Roger Penrose, who basically is asking the question, if entropy increases, then the state of the universe at the very beginning, the initial conditions, must have been a very low entropy. How can it be that the initial conditions of the universe were so carefully chosen? And my answer to that, or at least the way I'm trying to answer it, it's not that it's carefully chosen. It's that it is obtained by the equilibrium of the resolution of a game that pinpoints the one conditions that are optimal under the principle of least action. That's the way I would put it. Did it answer your question in a way?
Yeah, thank you.
Yeah, all right, awesome. Thank you everybody for attending.